All right, good morning. I apologize that I can't be with you today. But today you're going to get quite a bit of time to work on your syllabus homework. But I want to go through briefly where we've been. So first of all, last class we defined this idea of simple harmonic motion, which I'm just going to abbreviate SHM. And simple harmonic motion was motion that repeated due to a restoring force. And we had a couple equations with that, right? We said that when we're thinking about things that undergo simple harmonic motion, the first one we've been talking about is a spring. We said that the force on a spring is negative kx, where k is the spring constant or the stiffness of the spring. And then we also found, or said, and we're going to derive it today, but we said that the period of a spring is given by the equation 2 pi square root of m over k. The other thing that we said was, although you'll need to memorize these, we said that period is defined as the time divided by the number of oscillations, and that frequency is defined as the reciprocal of that. And so that we also have two equations, that t is 1 over the frequency and frequency is 1 over the period. All right, so that's where we were at. And we said that simple harmonic motion repeats because the restoring force wants to pull the spring back to equilibrium, but then the inertia of the object carries it past, and then the spring pulls it back to equilibrium, and then the inertia carries it past, and then the restoring force pulls it back to equilibrium, and the inertia carries it past. And for good measure, the restoring force pulls it back to equilibrium, and then the inertia carries it past. But this is something that, in the absence of friction, would go on forever. Today I want to talk about the energy. So the energy in simple harmonic oscillators. All right, so we can already do this, right? If you remember, we've already discussed way back in the energy unit, we know what the potential energy of a spring is. So we already know that the potential energy of a spring is 1/2 kx squared. If you don't remember it, no big deal. But that was what we found out a while ago. So this is the potential energy of a spring. We also know that kinetic energy is 1/2 mv squared. Therefore, you could say that the total energy of a spring is going to be given by 1/2 k, the potential energy, plus the kinetic energy. What I want to do real quick is I want to show you how we use that information in order to get to this really strange looking equation. So I just gave this to you yesterday, but we didn't really talk about where it came from. So what I want to do is I want to show you where it comes from. Okay, so how are we going to do this? So let's derive the equation for period of a spring, and we'll put an exclamation point here because it's fun. Okay, so first of all, we got to think about how we're going to do this. So a spring